Is my video conferencing application secure? Changes to the software are made at the speed of light. How can I continuously check the security? What do I even look for? I'm Betty Dubois, and I captured the packets during a video conference with my Endace probe. I have it capturing continuously between the firewall and internet router. To discover exactly how secure this meeting was, we're going to look at 4 items. Number 1, traffic patterns. Number 2, protocols. Number 3, encryption methods. And then finally, cipher suites. In this example, we're going to take a look at Zoom, but the same approach could be used to look at other services such as Microsoft Teams, GoToMeeting, Cisco WebEx, or any of the conferencing platforms. Let's start with protocols. According to Zoom's documentation, 9 different ports need to be opened on the firewall. Let's see which ones they actually use. Here in the traffic breakdown tool, Zoom is listed as one of the applications. I've already filtered for my IP address and the start and stop time of the Zoom video conference. Endace uses deep packet inspection to quantify applications, and we can use that as another filter. The Conversations tool shows that Zoom uses TLS sessions on TCP port 443, but the volume of data is small, especially considering the 7-minute screen share we did. We need to account for what's left. Audio normally runs on UDP, so let's add UDP back into the applications. Well, the UDP lines up perfectly from a time perspective. There must be audio and video in there. Check out Conversations. There are 3 streams with high data counts. 8801 is another one of the ports that Zoom says has to be open on the firewall. I've been using Zoom for years and already had it open on mine. Now we know which protocols are in use. TLS on TCP for the control, and UDP port 8801 for the audio, video, and screen share. Second, I want to know what the traffic patterns are. Who talks to who? Our goal is to find the IP addresses I spoke to during the meeting. We can filter for Zoom in the application and then check the list in Conversations. Notice most of the server addresses are AWS and CloudFront. Using cloud servers has been great to keep up with the increasing capacity demands, but it also means the IP addresses will change on a whim. There's an address that's not resolving. However, it is on Zoom's list. We can check to see what the server name is in the client hello. I'll add the IP address to my filter and launch Wireshark. I'm going to import my TLS profile. That way I have all of my filters and my columns. Now I just have to do a filter for the TLS handshake type equal to 1. This is a full-blown version of Wireshark running as an instance on the probe. It works just like Wireshark on the desktop. Great, all Zoom servers. I did a quick check on Aaron, and the address that we filtered for is for Oracle Cloud. All of the addresses spoken to were based here in the States. However, it's good to confirm where your data is going. But what about encryption? Well, obviously TLS is encrypted, so we love that. But what about the 8801 traffic? I'll change the filter to 8801 and put it back to just my IP address. Then we can launch Wireshark. There's no dissector for the proprietary protocol that Zoom uses, which is based on encrypted RTP. But it's not standard secure RTP, or even standard RTP, and there's little documentation for it. Let's check it out and follow the stream. With the exception of a few setup fields in the beginning, the 8801 traffic is encrypted. What encryption schemes does Zoom use? Zoom's documentation states all meeting data sent over UDP is encrypted with AES in GCM mode. Yet according to the article I'll link below, it's actually AES in ECB mode instead. For the TLS traffic, I'll go back to my Zoom filter and launch Wireshark. Now we can use the Server Hello button and see the cipher suite chosen by the server for each of the Zoom conversations. Two servers use different cipher suites than the others, but that's because they're using TLS 1.3 versus 1.2. TLS AES 128 GCM SHA-256 is the minimum for TLS 1.3 versus the recommended TLS AES 256 GCM SHA-256. The servers which support TLS 1.2 use TLS elliptical curves Diffie-Hellman RSA with AES, either 128 or 256 GCM SHA-384. These are all good cipher suites, according to SSL Labs. What did we learn? Sometimes vendors ask you to open more ports on the firewall than really necessary. Of course, we knew that. We got to see how easy it was to do everything we needed to on the probe versus downloading all of the packets. On the flip side, we were able to use Wireshark directly on the probe to see TLS server names, encrypted versus non-encrypted data, and to find out which cipher suites were chosen by the server in TLS. It's all there in the packets. We just had to look. This method can be repeated if you switch to another video conferencing platform or periodically to verify compliance. Let's see how they did on a security report card. Opening unnecessary ports. D. Zoom lists 9 ports to open, and we only used 2. Now perhaps some of them are used by apps besides the voice, video, chat, and screen share that we used in my meeting. The docs don't list which app uses which port. Although the documentation lists 9 ports that are required to be open for successful use of the service, an examination of the traffic patterns shows that not all of these ports are used. As a result, if you follow the docs, you might be opening unnecessary ports, and that might introduce a potential attack vector or vulnerability. Data encryption on. C. Although the session data is encrypted for chat and control traffic, the UDP is encrypted with a proprietary protocol, making it difficult to monitor. A person in the middle attack could presumably access this traffic and reconstruct the audio and video content that was sent. Strongest ciphers used. B-. The cipher used varied depending on the server being accessed. In some cases, TLS 1.3 was used, but in some cases the conversation used weaker TLS 1.2 encryption. Where the data is going. A. In this Zoom session, all the conversations happen between US-based servers, which is encouraging. However, it would be interesting to see what happens when the call involves international participants. And of course, you'd want to keep an eye on an ongoing basis as to where the data is going, as this could change. In summary, from what we were able to see using packet analysis, the data is encrypted, but the proprietary encryption of the video and audio content is a potential vulnerability. Likewise, as with any cloud service, you're not necessarily in control of where the data is sent or stored. Examining the packets can help you ascertain this. Do you have a packet mystery you'd like me to solve? Tell me about it in the comments below, and maybe it will inspire the next chapter of Packet Detectives.